Here's an example of a frame. We have here a member that is pin supported at A. We have one continuous member that goes up to B, turns 90 degrees, and goes to C. So that L shape is like one solid member. And then there's a hinge right here at C. What was I talking about on that previous slide with hinges? And then here we have a member that's spanning from the hinge, and then it goes down to this pin support at D. It's at an 80-degree angle to the horizontal. The dimensions are shown. We have a triangular distributed load here, starting at 0 and ending at 150 pounds per foot up at the top. This height is 9 feet for both sides. And then we have a downward force of 200 pounds at the mid-span of this portion here, BC, which is 4 feet wide. What are the reactions at A? I want to know what the reactions are over here. So here's a free body of the entire structure showing our reactions. Since they're pins, there's an RAX, an RAY, there's an RDX, and an RDY. That's 4 unknowns. We have 3 equations of equilibrium to solve for this because it's a 2D frame. So we have sum of forces in the X, sum of forces in the Y, and sum of moments about Z. We have too many unknowns for our equations. So we need some help. And what is that help? Remember the hinge. Okay. This member here, matter of fact, CD, we actually know it to be a two-force member because it is hinged at both ends and it does not have any forces acting on it along its length. So we know CD is going to either be in axial tension or in compression. My gut's going to tell me it's in compression. The beauty of that is we know the orientation of this internal force. We know that point C is going to be pushed up with a force that's right acting along the length of this member. For that matter, we actually know the resultant reaction down here at D is going to be in that same orientation. So we could actually turn these two components into one overall resultant because we know the orientation of the resultant. But that's not really the question that this problem asks. It's asking what are the reactions at A. So we're just going to use what we know about this hinge to help us. Okay, so here is my free body diagram that I've got. I'm solving for the reactions at A, so I'm going to keep the left-hand side. And remember my 3 rules of free body diagrams. I'm going to keep the part that I'm keeping. It's going to be these 2 unknown reactions down here. That's what I'm looking for. That's what my answers are going to be. And I chose RAX to point to the left, RAY to point up. I don't know if those are right or not. We'll see soon enough. I have a good feeling about RAX considering this is pushing that way. I'm not sure what's going to win out of these 2, but we'll see. But you make an assumption and you go with it. I kept the part that I'm keeping. I've kept the distributed load. I've kept the 200-pound point load pointing down. I've kept my dimensions. Everything is on this free body that I need to work with. I got rid of the part that I'm getting rid of. This member here, this two-force member, and its reaction over here at the far end, and the reaction vectors that were there. All that goes away. And at the cut surface, I've replaced what I've cut away with the internal force vectors that develop. And that's, remember, why I'm cutting at the hinge. It's really important to cut at the hinge because this is the only unknown vector right here. It's this force, the axial force from the two-force member. So I'm going to call it FCD. You can call it whatever you like. And it's acting at the same orientation. It's acting at that 80-degree angle to the horizontal, as the same as the orientation of the two-force member itself. Okay. Now I've done a little bit more work here. I've shown my X and Y component of this vector, FCD. So that's, the vertical component here would be what? FCD times the sine of 80 degrees. And this one's going to be FCD times the cosine of 80 degrees up here from the X. And they're both acting right there at the hinge. I've also found the resultant of this triangular distributed load as the area under the curve. So 1/2 base times height, or 1/2 times 9 feet times 150 pounds per foot. That's going to give me 450 pounds. And recalling what I know about centroids, because I know the resultant is acting at the centroid. I know that it is 2/3 of the distance from the pointy end of a right triangle, or 1/3 from the other end, whichever way you want to think about it, because that is where the centroid is. So it is 6 feet from the pointy end, as I have it mentioned here. And I draw that as a squiggly arrow to differentiate it from the distributed load so I don't accidentally count them twice. The resultant here is a retelling of this distributed load. It's not in addition to it. Likewise, my components over here I drew as dashed lines. I mean, you can do it however you want, but try to have some kind of system so you don't double count loads or forget to count loads. So I have 3 unknowns, RAY, RAX, and FCD, and that's really cool, but I don't know any of those. That's fine. That's what I'm here to figure out. I have 3 equations for 3 unknowns, so I should be able to solve this. If I look at sum of forces in the X, RAX and the X component of FCD are both unknowns. Same thing would be true for Y, RAY and the Y component of FCD. So those are both kind of a bust. I need to go to a moment equation first. And that's really why I chose the hinge to cut at, because, you know, hinges don't have an internal moment there. They are frictionless hinges. So it allows free rotation at the hinge. So whenever you have a hinge, you know that all you have to do is put the applied force vectors. There's no moment vector there that would be on it. So that was crucial to pick the hinge. That's what I mentioned back in the strategies for solving frames and machines in the lecture video. So that's really important that I cut there. Where I sum the moments about now, you know, what point I sum them about is up to me. If I picked the hinge to build my summation of moments about, it would get rid of FCD, but then I'd have RAX and RAY, which are both unknowns. So I'd have one equation with 2 unknowns, and that's not helpful either. So I think what I want to do is sum moments about A so that neither one of the reaction vectors play a part yet. I do want them. That is the goal of what I'm doing here. I'm looking at for the reactions at A, but I can't get them in one step. I need to go ahead and solve for FCD and then apply sum of forces in the X and sum of forces in the Y, and then I can get it. So here is my summation of moments about A. I'm going to say counterclockwise is positive. So that's equal to 0. I've got my FCD times cosine of 80. That's going to be the X component of FCD, and that is acting at 9 feet away from A, and that's positive because it's counterclockwise. And then I've got FCD times the sine of 80, which is this vertical component right here. It's going to be times 4 feet, because that's how far away from A it is, and it's also positive because it's also counterclockwise. And then I've got this 200-pound force here acting down, and it's 2 feet away from A, and it's going to want to cause a clockwise rotation, so that's why it's going to have a negative sign. And then I've got my resultant here, 450 pounds acting at 6 feet away from A. So when I do all that math, I get that FCD, value up here, is 563.4 pounds. So I can label that on my free body and go to my next step. And honestly, it doesn't really matter at this point. You could do some forces in the Y first or some forces in the X first, because you're just going to get answers out of both of them. I'm going to do X first here. I'm going to say to the right is positive. So I'm going to have minus 563.4 pounds times the cosine of 80. That's going to give me the X component here. Plus 450 minus RAX equals 0. That tells me that RAX is 352 pounds. One of my answers. And then summing forces in the Y, up positive, I have 563.4 times the sine of 80, which is my vertical component, minus 200 pounds, don't forget about the applied force up here, plus RAY equals 0, and I get that RAY is equal to minus 355 pounds. What does that mean? Well, it means I got the right assumption for RAX, that it is pointing left because I got a positive number. RAY turned out to be negative, which means my assumption was wrong. It's actually pointing down. I'm not going to change anything, because if you change, you erase your vector and draw it the other way, then none of your math in any of your equations supports that anymore. So I would just leave it like it is and say RAY is equal to minus 355 pounds. You could also then say, in parentheses, equal to 355 pounds down, and draw a down arrow, whatever works for you, that's fine. But that way it's all perfectly clear when you go back to check over your work or you submit it to somebody else. It's really obvious what that means. So that's a example of a frame analysis, finding reactions. Thanks.